Hello everyone. In this session, we will see how the causality and stability of the system is analyzed with the help of Z transform. A linear time invariant discrete time system is said to be causal only if impulse response, that means h of n, is 0 for n less than 0. Such kind of systems are said to be right hand sided system. The ROC of the causal system will lie exterior of the circle, and also the degree of the numerator polynomial is less than or equal to the degree of the denominator polynomial of a system function. Similarly, a linear time invariant discrete time system is said to be stable only if impulse response of the system is finite. That means summation n equal to minus infinity to plus infinity modulus of h of n is less than infinity. Such kind of systems are said to be stable system. Otherwise, a system is said to be unstable system. For a linear time-invariant stable system, the poles of the system will lie inside the unit Z circle. If it lies outside the unit Z circle, means such kind of systems are said to be unstable. If it is exactly lies on the boundary of the circle, means that kind of systems are said to be marginally stable. Now we will see the relationship between the stability of the system and the location of the poles. Figure A shows the stable system where the cross mark represents the location of the pole. The pole of the first system lies inside the unit scissor circle, so the system is said to be bounded input and bounded output. So system is said to be bifostable system. When you see the second system, the cross mark exactly lies on the boundary of the unit Z circle. That means pole lies on the boundary of the unit Z circle. So the system is said to be marginally stable system. When you see the figure C where the pole lies outside the unit Z circle, so the system is said to be unstable system. When we look into the figure D, where the pole lies on the negative side of the Z circle, but it lies inside the unit Z circle, so the system is said to be stable system. When we see the fifth figure, that means figure E, a system is said to be marginally stable system because the pole exactly lies on the boundary of unit Z circle. Now we'll discuss some of the example problems of causality of the system. Let us consider the first problem. Here the given system function is h of z equal to z cube plus 4z square plus z by 2z square plus 5z plus 1. When we look into the numerator polynomial, the degree of the numerator polynomial is greater than the degree of the denominator polynomial. So the system is said to be a non-causal system. Now we will analyze the second problem where the system function is given as h of z is equal to z minus 1 into z plus 2 by z minus 1 by 2 into z minus 3 by 4 and ROC greater than 3 by 4. When we look this system, there are two poles of the system. One is 1 by 2, another one is 3 by 4, and the ROC of the system is greater than 3 by 4. So the ROC lies outside of the highest pole. So the system is said to be a causal system. When we look into the third problem, the system function is h of z is equal to z minus 1 into z plus 2 divided by z minus 1 by 2 into z minus 3 by 4. There are two poles. One is 1 by 2, another pole is 3 by 4, and the ROC is less than 1 by 2. So the ROC is less than the highest pole. So system is said to be non-causal system. The system function of the second problem is given as h of z is equal to 2 minus 13 by 4 z inverse by 1 minus 1 by 4 z inverse into 1 minus 3 z inverse. Determine the causality and stability of the system for following ROC cases. First case is ROC greater than 3, second case is ROC less than 1 by 4, and third case is ROC lies between 1 by 4 and 3. Now we have to rearrange the terms of the system function. Finally, we will get h of z is equal to z into 2z minus 13 by 4 by z minus 1 by 4 into z minus 3. The first condition is region of convergence z greater than 3. For this condition, The ROC lies exterior of the circle, so the system is said to be causal. And when we look into the poles of the system, not all the poles lies inside the unit scissor circle, so the system is said to be unstable system. So for the given first condition, system becomes causal and unstable. For the second condition, ROC less than 1 by 4. In that case, the ROC of the interior of the circle passing through the innermost pole of the h of z. So the system is non-causal. Similarly, the ROC does not include the unit z circle. So the system is said to be unstable system. For the given third condition, ROC is between 1 by 4 and 3. For this condition, the ROC is to the left side of the outermost pole and to the right of the innermost pole. Hence, the system is said to be non-causal. Similarly, the ROC includes unit Z circle. So, the system is said to be a stable system. For the given third condition, the system is non-causal and stable system. The system function is given by h of z is equal to z by z minus 1 by 4 into z plus 1 by 4 into z minus 1 by 2. For different possible ROCs, determine the causality and impulse response of the system. When we look into these poles of the system, the different possible ROC conditions are: first one is ROC greater than 1 by 2, second one is ROC less than 1 by 4, and the third one is ROC will lie between 1 by 4 and 1 by 2. So in order to find out the impulse response of the system, first we need to apply the partial fraction and we need to find out the values of A1, A2, A3. When we solve the partial fraction, we will get the A1 value as minus 8 and A2 value as 8 by 3 and A3 value as 16 by 3. And we need to substitute the obtained values of A1, A2, A3 in system function expression, so that we will get h of z is equal to 8z by z minus 1 by 4 plus 8 by 3 z by z plus 1 by 4 plus 16 by 3 into z by z minus 1 by 2. The first ROC condition is z greater than 1 by 2. For the given ROC condition, the impulse response h of n is right hand sided sequence and hence h of z is a causal sequence. Since system ROC includes unit circle and all poles lies inside the unit circle, so the system is said to be a stable system. When we see the figure 1a, all the poles of the system lies inside the unit z circle and ROC lies exterior of the circle. So the system is said to be a causal and stable system. For the second ROC condition z less than 1 by 4, the ROC is interior of the circle passing through the innermost pole. Hence, the system is said to be non-causal system. Similarly, the unit z circle does not include all the poles. So, the system is said to be a unstable system. Finally, for the second condition, the system is non-causal and unstable. As per figure 1b, the ROC does not lies outside the outermost pole, so the system is said to be non-causal. Similarly, ROC does not include all the poles, so system is said to be unstable. The third ROC condition is ROC lies between 1 by 4 and 1 by 2. As per the given ROC condition, the ROC does not lies on the right side of the pole, so the system is non-causal. Similarly, ROC does not include all the poles, so the system is said to be unstable. For the given ROC condition, the pole zero diagram is plotted in figure 1c. As per this figure, the unit is a circle does not include all the poles, so the system is said to be unstable and non-causal.